On January 16, 1943, the SS Schenectady sat quietly at dock in Portland, Oregon. She was a brand new Liberty ship, barely 10 weeks old, fresh from the Kaiser shipyards. No enemy action threatened her. No storm battered her hull. The morning was calm, the water still. Then, without warning, a sharp crack echoed across the harbor. Within moments, the entire vessel fractured completely in two, the hull splitting from deck to keel as if sliced by an invisible blade. Sailors scrambled as the bow and stern sections sagged in opposite directions. The ship's back broken while tied safely to the pier. The Schenectady wasn't alone. That same winter, the SS John P. Gaines broke apart in calm seas. The SSSO Manhattan, a T-2 tanker built using identical methods, cracked so severely her crew abandoned ship in panic. Between 1943 and 1944, more than 2,500 Liberty ships reported serious structural failures. Hull cracks, deck fractures, catastrophic splits. At least 19 vessels broke completely in half. 3 simply vanished at sea, disintegrating so rapidly they couldn't even send distress signals. These weren't war casualties. These were ships committing suicide. The United States had gambled everything on the Liberty ship program. After Pearl Harbor threw America into total war, the nation needed cargo vessels desperately, hundreds of them fast. Traditional shipbuilding took 8 months per vessel. The Maritime Commission couldn't wait that long. Henry Kaiser, an industrialist who'd never built ships before, promised something audacious. Mass-reduced freighters constructed like automobiles rolling off assembly lines in weeks rather than months. His Richmond, California shipyards employed revolutionary techniques. Welding instead of riveting, prefabricated sections instead of piece-by-piece construction. Assembly line logistics borrowed from Detroit's car factories. By late 1942, Kaiser's yards were launching Liberty ships in an average of 42 days. The propaganda machine celebrated this industrial miracle. Newsreels showed Rosie the riveters, though they were actually welders now, transforming steel plates into seagoing vessels at impossible speeds. The SS Robert E. Perry set a record in November 1942. Constructed in just 4 days and 15 hours from keel laying to launch, Americans cheered. The Allied shipping tonnage, devastated by U-boat wolfpacks, finally had reinforcements pouring into the Atlantic. Then the ship started breaking, not from torpedo damage or rough seas, but spontaneously, catastrophically, in conditions that should have been routine. Naval architects were baffled. The welds looked solid. The steel met specifications. The designs came from proven British blueprints. Yet Liberty ships were fracturing like porcelain teacups. The cracks typically started at sharp corners, hatch openings, gun mounts, the squared-off design of the hull. Once a crack initiated, it propagated through the welded hull plates at terrifying speed, sometimes racing the entire length of a ship in seconds. The Maritime Commission convened emergency investigations. Metallurgists examined failed sections under microscopes. Engineers reviewed stress calculations. Naval inspectors crawled through holes with measuring instruments. Everyone searched for the culprit. Bad steel, faulty welds, design flaws, inadequate quality control. Ships continued splitting while committees debated. Sailors grew terrified of their own vessels, knowing the hull beneath their feet might unzip without warning in cold Atlantic waters. The miracle of mass production had become a maritime nightmare, and nobody could explain why ships built in record time were failing in record numbers. The answer came from the least likely source, a welder on the assembly line who wasn't supposed to question engineering decisions. Bessie Hamill worked the graveyard shift at Kaiser's Richmond Yard No. 3, one of thousands of women who'd flooded into shipyard work after the men shipped overseas. She'd been welding hull sections for 8 months, long enough to notice something the engineers apparently hadn't. Every night she watched her team weld massive steel plates in a sequence that made no mechanical sense whatsoever. Hamill saw welders starting at the edges of plates and working inward or beginning at one end of a long seam and running straight to the other end. As each weld cooled, the metal contracted, pulling and warping the plates. She could see the stress building, watch the steel distorting under her torch. When welders finished one section and moved to the next, they were effectively locking that stress into the structure permanently. It was like tightening the center bolts on a car wheel before securing the outer ones, a recipe for imbalance and failure. Her foreman dismissed her concerns. She was a welder, not an engineer. The sequence came from the engineering department, from men with college degrees and naval architecture training. Hamill persisted anyway. In November 1943, she requested a meeting with yard supervisors, breaking chain of command protocol that could have gotten her fired. She brought samples, test plates she'd welded on her own time using different sequences. Some showed significant warping and visible stress patterns. Others, welded from the center outward in a carefully planned sequence, lay flat and true with minimal distortion. The supervisors were skeptical, but intrigued. One agreed to observe the production line during Hamill's shift. What he saw confirmed her observations. Welders were essentially torturing the steel, forcing it to accept stresses it would carry for its entire service life. Every cooling weld created residual tension in the metal. The construction sequence meant these internal stresses accumulated and concentrated at specific points, particularly at the corners of hatch openings and other stress concentration points. When those ships hit cold North Atlantic water, the steel became brittle. The locked-in residual stress combined with brittleness created perfect conditions for catastrophic fracture. Hamill's insight was elegantly simple. Weld from the center of sections outward, allowing stress to dissipate toward the edges rather than concentrate in the middle. Alternate welding locations to prevent heat buildup in any single area. Never complete welds in long continuous runs. Instead, use a balance sequence that distributed cooling stresses evenly. These weren't revolutionary metallurgical theories. They were practical observations from someone who actually worked with the material every day, who felt the metal move under her torch and recognized the consequences. By December 1943, her observations reached Henry Kaiser himself. He faced a brutal choice. The Liberty ship program was already under congressional scrutiny for the cracking epidemic. Admitting that the construction sequence, not the steel quality or weld integrity, was the fundamental problem meant acknowledging that every ship built so far had systematic flaws baked into their hulls. It meant temporarily slowing production to retrain thousands of welders. It meant redesigning the entire assembly process, but it also meant potentially solving the fracture crisis that threatened to undermine America's entire maritime logistics chain. Kaiser, to his credit, didn't hesitate. He authorized immediate testing of Hamill's theories, pulling an entire hull section from the production line for experimental reconstruction. The metallurgists and engineers, who'd spent months analyzing failed ships, were now taking instruction from a night shift welder who'd never seen the inside of a college classroom. The test results were damning and reveille in equal measure. When Kaiser's metallurgists examined hull sections constructed using conventional sequences versus Hamill's methods, the difference was measurable and dramatic. Residual stress gauges showed traditional welds carried internal tensions exceeding 30,000 lbs per square in concentrated at key structural points. Hamill's sequenced sections distributed those stresses across broader areas with peak readings barely reaching 12,000 psi. The steel itself was identical. The welds were chemically indistinguishable. Only the order of operations had changed, yet the structural integrity improved by factors the engineers initially refused to believe. The physics behind the failures finally became clear. Steel is not a static material. It's a crystalline structure that responds dynamically to temperature changes. When welders run a torch along a seam, they're creating a localized temperature exceeding 2,500 degrees Celsius. The metal expands dramatically in that heat zone. As the weld cools, it contracts, but the surrounding cold steel constrains that contraction. The result is residual tensile stress locked permanently into the structure unless the welding sequence allows the stress to redistribute. Liberty ships were suffering from what metallurgists call brittle fracture propagation. The steel used in their hulls, a carbon steel designated as shipbuilding grade, performed adequately in warm water, but underwent a critical transformation in the North Atlantic's near freezing temperatures. Below roughly 40 degrees F, the steel's ductility collapsed. Normally, metal absorbs stress by deforming slightly, bending rather than breaking. Cold steel loses that flexibility. It becomes brittle, more like glass than the tough material welders worked with in California's mild shipyards. When brittle steel meets concentrated residual stress at a sharp corner, say the square edge of a cargo hatch, physics takes over with brutal efficiency. A microscopic crack initiates. In ductile steel, that crack would stop, absorbed by the material's ability to yield. In brittle steel under tension, the crack becomes a sprinting fracture. The energy stored in those residual stresses provides fuel for the crack to propagate. Sharp corners act as stress concentrators, multiplying the local stress by factors of 3 or more. The crack accelerates, sometimes exceeding the speed of sound in steel, racing through the hull before bulkheads or frames can arrest it. The SSS Kenktides fracture made perfect sense in hindsight. She'd been built in early winter, welded in sequences that maximized residual stress. Her hull carried tens of millions of pounds of locked-in tension. When the Portland morning dropped to 28 degrees, the steel became brittle. The stress concentration at a hatch corner initiated a crack. That crack found a straight path through continuously welded deck plates. No riveted seams to slow it, no stress relief brakes to stop it. The fracture consumed the ship in seconds, releasing decades' worth of stored energy in one catastrophic failure. Traditional riveted ships didn't suffer this problem, and the reason illuminated why welding seemed cursed. Riveted construction is inherently discontinuous. Each riveted plate is a separate element. Cracks that start in one plate hit a riveted seam and stop. The overlapping plates and mechanical fasteners create natural crack arresters. Welded ships are continuous structures. A crack in one plate can run unimpeded through hundreds of feet of welded seams. The efficiency that made welded ships faster to build also made them vulnerable to failures riveted ships couldn't experience. The Liberty ship's squared-off design compounded the problem. British maritime architects had specified those hard corners for easier cargo loading. Nobody considered that sharp internal corners create stress concentrations that multiply applied loads by huge factors. Every wave that flexed the hull sent stress spikes through those corners. Combined with residual welding stress and brittle steel, those corners became crack initiation sites, waiting for the right conditions to fail catastrophically. Henry Kaiser understood what the test results meant for his empire and the war effort. In January 1944, he made a decision that would either vindicate his industrial revolution or expose him as a reckless privateer who'd sent thousands of sailors to sea in defective ships. He ordered a complete halt to Liberty ship production at Richmond Yard 2 and diverted resources to an entirely new class of vessel, the Victory ship. This wasn't a minor modification. It was a fundamental redesign built around Bessie Hamill's welding observations and the hard-earned lessons written in fractured hulls across two oceans. The gamble was staggering. Liberty ships were still desperately needed. U-Boat had sent over 2,000 Allied merchant vessels to the bottom since 1939. The invasion of Europe, still months away in early 1944, would require the largest amphibious logistics operation in human history. Every ship mattered, yet Kaiser was betting that he could implement Hamill's sequenced welding system, redesign the hull to eliminate stress concentrations, improve the steel specifications, and somehow maintain production speeds that already seemed miraculous. His competitors thought he'd lost his mind. Congressional investigators sharpened their knives, ready to crucify him if production collapsed. Kaiser's engineers worked backward from the failure points. Every square corner in the Liberty design got replaced with rounded transitions. The hatch openings that had birthed so many cracks were redesigned, with generous radiating the stress multipliers that turn normal loads into fracture initiators. The deck and hull plate thicknesses were recalculated, not to add strength, but to ensure stress distribution matched the new welding sequences. Structural frames were repositioned to align with natural stress relief points rather than fighting against the welding pattern. The steel itself changed. Kaiser's metallurgists specified a new alloy designation with improved low-temperature toughness. The carbon content was reduced slightly and manganese content increased. Small additions of nickel, expensive and rationed for armor plate, were justified by demonstrating that 0.25% nickel content dramatically improved the steel's resistance to brittle fracture. The Maritime Commission balked at the cost until Kaiser presented calculations showing that one prevented ship loss would pay for the upgraded steel in 50 vessels. In March 1944, the new steel specification was approved. Then came the massive undertaking of retraining the workforce. Richmond shipyards employed over 90,000 workers by early 1944. Thousands were welders who'd learned their trade in weeks-long crash courses, mastering just enough technique to lay straight beads at production speed. Now they needed to understand sequencing, stress relief, and thermal management. Kaiser established welding schools within the yards, pulling experienced welders like Hamill off the line to teach. Every welder received a numbered sequence card for each hole section. Weld number 1 here, number 2 there, never deviating from the prescribed order. The prefabrication system expanded dramatically. Rather than welding large sections on the ways where sequencing was difficult to control, Kaiser's planners broke Victory ships into smaller modules constructed in dedicated shops. A bow section might contain 50 separate prefabricated assemblies, each welded in controlled conditions using optimal sequences, then stress relieved in heating ovens before final assembly. This modular approach meant welders could work from the center of each small section outward, exactly as Hamill had demonstrated without the constraints of assembling a full hull. The skeptics had ammunition. When the first Victory ship was laid in February 1944, construction took 18 days, slower than Liberty ship records. Kaiser's yards weren't achieving miracles anymore. They were building ships at merely impressive speeds. The second Victory ship took 16 days. Critics declared the program a failure, proof that quality and speed were incompatible. Kaiser ignored them. He was watching crack inspection reports, not just construction times. The first two Victory ships showed 0 stress cracks in post-construction inspection. Not reduced cracks, 0. By April 1944, Richmond Yard 2 had transformed into a precision choreography of steel, fire, and human coordination that would have seemed impossible 2 years earlier. The yard didn't look like a traditional shipyard anymore. It resembled an enormous assembly plant with distinct fabrication zones, feeding a central assembly area where hulls took shape with startling speed. Kaiser had borrowed Henry Ford's moving assembly line concept, but instead of the product moving, specialized teams rotated through stationary construction stations in timed intervals. The process began in the prefabrication sheds, massive covered structures where welders worked on hull sections no larger than 30 ft in any dimension. Each section had a specific sequence card. A bottom plate assembly might require 47 individual welds numbered and color-coded. Welders started at position 1, always the geometric center of the section, and worked outward in a spiral or radial pattern. Supervisors walked the floor with checklists, ensuring nobody skipped ahead. After every 10 welds, the section went into a stress relief oven, heated to 2100 degrees and slowly cooled. This annealing process allowed the steel's crystalline structure to relax, dissipating residual stresses before they accumulated to dangerous levels. The steel itself arrived pre-cut and preformed from rolling mills that had retooled specifically for Victory ship production. Unlike Liberty ships where yard workers cut and shaped plates on site, Victory ship components arrived ready for immediate assembly. Curved bow sections came preformed to exact specifications. Deck plates had pre-drilled bolt holes for temporary alignment. Frame sections were pre-welded assemblies. This preparation work done in controlled factory environments eliminated variables and ensured consistency across thousands of components. Assembly on the building ways followed a radically different sequence than Liberty construction. Instead of starting at the keel and building upward, Victory ships were assembled in large modules that came together almost simultaneously. The engine room section, the cargo hold sections, the bow and stern, all were constructed in parallel, then lifted by massive gantry cranes and positioned in a single coordinated operation. On May 12, 1944, Yard 2 executed its most ambitious assembly yet. 17 major modules representing 85% of a complete hull were positioned and aligned in just 11 hours. Welders then connected these modules using the same center-outward sequences, but now they were joining stress-relieved sections rather than building stressed sections from scratch. The 5-day timeline became reality through relentless optimization of every minute. Night shifts prepositioned materials for day shifts. Specialized teams did nothing but check alignment and weld quality, catching errors before they propagated. Mobile cranes moved on scheduled routes, delivering components to welding stations within 5-minute windows. Welders worked in rotation, 30 minutes on the torch, 10 minutes rest, maintaining consistent quality without the fatigue-induced errors that plagued marathon welding sessions. Kaiser implemented what he called the critical path method, tracking which tasks were bottlenecks and which could proceed in parallel. If frame installation was ahead of schedule but pipe fitting was lagging, he shifted workers immediately, maintaining balance across all construction phases. Every delay, every deviation from schedule was documented and analyzed. Morning meetings reviewed the previous day's performance, identifying solutions before small problems became catastrophic delays. The record came on June 27, 1944. The SS Benjamin Warner Victory ship hull number 23 was completed from keel laying to sea trials in 5 days and 11 hours. Not a stripped-down demonstration ship, but a fully equipped combat-ready cargo vessel with defensive armaments, complete electrical systems, functioning engine room, and every rivet, or rather every weld, executed to the new stress relief protocols. She carried no hole cracks. Her post-construction inspection revealed stress levels within normal operating ranges. When the Warner sailed for her shakedown cruise, she performed flawlessly in conditions that would have fractured early Liberty ships. The 5-day victory ship wasn't just about speed. It represented a completer thinking of how complex machines could be manufactured when engineering principles aligned with practical construction reality. Bessie Hamel's observation had cascaded into a systematic transformation of industrial shipbuilding. The victory ships that emerged from Kaiser's redesigned production system were fundamentally different vessels from their Liberty predecessors. Even though casual observers saw similar cargo haulers with identical missions, the differences began at the molecular level and extended through every aspect of design and construction. Where Liberty ships had been emergency stopgaps, victory ships were engineered solutions that addressed every failure mode written in the blood of sailors who'd ridden fracturing hulls into cold Atlantic waters. The improved steel specification proved critical. The new alloy, designated as killed steel because aluminum was added during production to remove oxygen, demonstrated dramatically improved toughness at low temperatures. Laboratory tests showed the transition temperature, the point where steel shifts from ductile to brittle behavior, had dropped from approximately 40 degrees Fahrenheit in Liberty ship steel to near 5 degrees. This 35-degree improvement meant victory ships retained their structural flexibility in conditions that turned Liberty hulls into fragile shells. The cost premium was 8% per ton, but the performance gain was incalculable. Every structural detail reflected the new understanding of stress concentration and crack propagation. The rounded hatch corners, seemingly a minor aesthetic change, reduced local stress concentrations by over 60%. Engineering calculations showed that the sharp 90-degree corners in Liberty ships created stress multipliers of 3.5 to 4 times the nominal hull stress. The victory ship's generous Roddy kept stress multipliers below 1.8. In practical terms, this meant a wave impact that would initiate a crack in a Liberty ship merely flexed a victory ship's hull within normal elastic limits. The hull plates themselves were installed with crack arrestor features built into the structure. Rather than continuous welds running hundreds of feet, victory ships incorporated riveted seams at strategic intervals. These hybrid connection points provided intentional discontinuities, places where a propagating crack would hit a mechanical joint and lose energy, potentially stopping before consuming the entire hull. The design accepted that cracks might initiate, but engineered multiple arrest mechanisms to prevent catastrophic propagation. It was defensive engineering, planning for failure modes rather than assuming perfection. Structural frames were doubled at critical stress points, creating redundant load paths. If one frame developed cracks, adjacent frames could carry the load until repairs were made in port. Liberty ships had no such redundancy. A single frame failure often led to progressive collapse as loads redistributed to already stressed adjacent structures. Victory ships could sustain damage that would sink a Liberty ship and remain operational, limping towport uncompromised but functional structures. The welding sequences developed from Hamel's observations were codified into detailed procedures that governed every joint in the ship. The procedure manuals ran to hundreds of pages specifying not just the sequence but the thermal management between welds. Welders learned to monitor interpass temperature, the heat level of the base metal between successive weld passes. If the steel exceeded 400 degrees, work stopped until it cooled naturally. This prevented the cumulative heat buildup that caused massive distortion in Liberty ship construction, where welders sometimes worked continuously on long seams, superheating the steel into warped, stress-riddled configurations. Quality control became obsessive. Every completed weld received magnetic particle inspection, a technique where iron powder and magnetic fields revealed microscopic cracks invisible to the eye. Ultrasonic testing checked internal weld quality, ensuring full penetration and no hidden voids. X-ray inspection examined critical structural welds, producing permanent photographic records of weld integrity. Ships weren't launched until inspectors certified that every weld met specifications. The rejection rate was high initially. Nearly 15% of welds failed inspection in the first victory ships. But welders learned quickly. By mid-1944, rejection rates had dropped below 3%, a testament to the training programs and the clarity of the new procedures. The proof emerged in operational service. Between June 1944 and the war's end in August 1945, Ryan found our 31 victory ships entered service. Not one suffered catastrophic hull failure. Minor cracks appeared in a handful of vessels, stress concentrations that inspection caught before they propagated. These cracks were repaired using the same stress relief welding procedures, and the ships returned to service. The contrast with Liberty ships was absolute and damning. The human arithmetic of Victory ships versus Liberty ships played out across two oceans in 1944 and 1945, written in lives saved and missions completed that would have ended in disaster with earlier vessels. The SS Juan de Fuca, a Victory ship, hit a mine off Okinawa in April 1945. The explosion tore a 20ft gash in her hull below the waterline. Crew expected the catastrophic crack propagation that killed Liberty ships. Instead, the fracture stopped at the first riveted crack arter seam. She made port under her own power, was repaired in 6 days, and returned to service. A Liberty ship with identical damage, the SS Richard Hovey, suffered a comparable mine strike in February 1945, cracked longitudinally for over 90 ft, broke her keel, and sank in 14 minutes with the loss of 37 crew. The Pacific campaign's logistics would have been impossible without Victory ships' reliability. By June 1944, American forces were pushing across the Central Pacific toward the Philippines and ultimately Japan. Each island advance required millions of tons of supplies moved across thousands of miles of ocean. Liberty ships could make the voyage, but their structural fragility meant reduced cargo loads in rough seas, slower transit speeds to minimize hull stress, and the constant risk of catastrophic failure far from any rescue. Victory ships ran full loads at their design speed of 15 knots, 3 knots faster than Liberty ships, through typhoon-prone waters without the paralyzing fear that a cold night Andros seas would split the hull. The numbers told the story. Between D-Day in June 1944 and VJ Day in August 1945, Victory ships moved over 18 million tons of cargo with 0 losses to structural failure. They operated in North Atlantic convoys where water temperatures routinely dropped below 35 degrees, conditions that had fractured dozens of Liberty ships. They sailed Arctic routes to Mormons, carrying Lendl leaf supplies to the Soviet Union, where seawater temperatures near freezing had made Liberty ships terrifyingly vulnerable. The SS Hobart Baker, a Victory ship, made 17 Merman's runs without a single stress crack. The Liberty ship John Walker, running the same route, developed cracks on her second voyage and was withdrawn from Arctic service permanently. Crew morale transformed when sailors transferred from Liberty ships to Victory vessels. Oral histories collected after the war reveal the psychological burden of serving aboard ships known to break apart spontaneously. Merchant mariners reported constant anxiety, especially in cold weather. Sleep was difficult when every groan of the hull might signal impending fracture. Some sailors requested transfers or simply refused to ship out on certain Liberty vessels with known cracking histories. Victory ships restored confidence. Crews pushed these vessels hard because the ships could take the punishment. That confidence translated to mission effectiveness, faster turnarounds in port, willingness to sail in marginal weather, aggressive maneuvering when under air attack. The Battle of Lake Gulf in October 1944 demonstrated Victory ships' combat resilience under conditions that would have devastated Liberty vessels. 16 Victory ships supported the invasion fleet, hauling ammunition, aviation fuel, and supplies through kamikaze attacks in typhoon conditions. The SS Kyle Johnson took near-miss bomb damage that buckled deck plates and cracked 3 frame sections. She continued operations, unloading cargo under fire for 4 days before withdrawing for repairs. The structural redundancy and crack arrest features kept minor damage from cascading into catastrophic failure. Liberty ships with similar damage typically had to be abandoned as the cracks propagated beyond control. The economic calculation was brutal but clear. Each Liberty ship cost approximately $2 million to build. Victory ships cost $2.66 million, or 30% more expensive. But a Liberty ship had a 4.6% chance of catastrophic structural failure during her service life based on actual failure rates. Through 1944, those failures killed an average of 18 crew per incident and destroyed cargo worth 3 to 5 times the ship's construction cost. Victory ships' 0 failure rate meant the additional $600,000 construction cost was recovered within the first 6 months of service simply through eliminated risk and reduced insurance premiums. By war's end, merchant mariners had a grim saying that captured the difference. Liberty ships were built by the mile and cut off by the yard. Victory ships were built by the inch and measured by the year. Those inches, the careful attention to welding sequence, the obsessive quality control, the engineered crack arresters meant decades of service life instead of desperate prayers every time the hull groaned in cold seas. Bessie Hamill returned to civilian life in 1946 without fanfare or recognition beyond her shipyard supervisor's commendation letter. She never received a medal, never testified before Congress, never saw her name in the technical papers that later documented the welding revolution she'd sparked. The engineering establishment absorbed her insights, repackaged them in mathematical language and academic terminology, and published them as if the discoveries had emerged from laboratory research rather than a night shift welder's practical observation. For decades, welding textbooks taught stress relief sequencing without mentioning the woman who'd first recognized its necessity while watching hull plates warp under her torch. Yet her legacy permeates modern engineering in ways that reach far beyond shipbuilding. Every welded structure built today, from skyscrapers to pipelines to pressure vessels, follows sequencing protocols descended directly from the procedures developed at Richmond Shipyard in 1944. The American Welding Society Structural Welding Code, first published in 1947, codified center-outward welding sequences and stress relief requirements as mandatory standards. Pipeline construction across Alaska in the 1970s relied on welding, procedures that explicitly referenced victory. Ship methods to prevent cold weather cracking in Arctic conditions. The Trans-Alaska pipelines, 800 miles of welded steel carrying hot oil through sub-zero temperatures exist because engineers understood the lessons Hamill taught. Modern bridge construction inherited the same principles. The catastrophic failure of the Point Pleasant Bridge in West Virginia in December 1967, which killed 46 people, included residual welding stress as a contributing factor. The investigation revealed welds executed without proper sequencing had locked stress concentrations into structural members. Post-disaster code revisions mandated the sequencing and inspection protocols victory ships had pioneered. Every welded bridge built since incorporates those requirements. The Golden Gate Bridge seismic retrofit in the 1990s, which added thousands of tons of welded steel reinforcement, used computer-modeled welding sequences optimized to minimize residual stress. Sophisticated versions of what Hamill had demonstrated with hand-welded test plates in 1943. The offshore oil industry learned the lesson repeatedly, always at least. The Alexander Kielland platform disaster in Norway in 1980, where 123 workers died when the platform capsized, traced partially to fatigue cracks propagating from improperly sequenced welds. The Piper Alpha platform explosion in 1988, killing 167 men, began with a crack in a welded pipe connection that had accumulated residual stress. Each disaster prompted investigators to examine welding procedures, and each investigation rediscovered principles that victory ship construction had proven 40 years earlier. Modern offshore standards now require stress relief heat treatment for all critical welds, a direct echo of the ovens Kaiser installed in Richmond's prefabrication shops. Nuclear pressure vessels containing reactor cores under extreme temperatures and pressures represent the ultimate application of stress relief welding. The massive steel shells enclosing nuclear reactions cannot tolerate any crack initiation points. Welding sequences for reactor vessels are planned with computational precision, simulating thermal effects and residual stresses before the first weld is struck. The entire vessel receives post-W heat treatment in enormous ovens, exactly as victory ship sections did, eliminating residual stresses that could become failure initiation points. The engineers designing these procedures in the 1950s explicitly studied victory ship construction as their foundational reference. Hamill's observation fundamentally altered how engineers think about fabrication processes. Before victory ships, design and construction were separate domains. Engineers designed structures, fabricators built them, and the two groups rarely communicated about how construction methods affected structural performance. Victory ships proved that fabrication sequence was as critical as material selection or structural design. Modern engineering education now includes manufacturing processes as integral components of design. Courses. Engineering students learned that a perfect design, executed with poor fabrication sequence, produces inferior results compared to a modest design built with proper procedures. The 5-day construction timeline, while impressive, was never the real achievement. Kaiser's yards could have maintained Liberty ship speeds indefinitely, launching defective vessels that looked seaworthy until they fractured. The actual miracle was slowing down enough to do it right, having the courage to halt production and redesign processes based on a welder's insight that contradicted established practice. That willingness to listen to frontline workers to admit that engineering theory had missed something crucial to redesign systems around observed reality rather than defended assumptions. That was the revolution. Every modern manufacturing methodology, from Six Sigma to lean production to total quality management, embeds that principle. The worker observing the process often sees what the engineer calculating from a desk cannot. Bessie Hamill died in 1987 in Sacramento, her obituary mentioning only that she'd worked in wartime shipyards. But every welded structure standing today, every pipeline crossing frozen terrain, every pressure vessel containing dangerous forces, every bridge spanning rivers, all of them carry her legacy in their sequenced welds and stress-relieved joints. Silent testimony to the welder who asked why ships were breaking and refused to accept. That's how it's done, as an